Welcome to the 9th example in our WinderCAM tutorial series. Today we are looking at something unusual, not a composite pressure vessel or a rocket nozzle, but a rubber compensator for a large diameter pipeline.
This is an interesting case because it combines two different technologies, rubber processing and composite reinforcement. The compensator consists of alternating layers of uncured rubber tape and reinforcing cord mesh made from polymer strands.
So it's like a hybrid structure.
Exactly. The rubber tape is relatively wide. After vulcanization, it transforms into a solid, durable rubber matrix. The cord mesh provides the structural reinforcement, much like in traditional composites. Together, they form a flexible but strong connection between two pipe sections, capable of absorbing thermal expansion and vibration.
How does WinderCAM handle this geometry?
The modeling process follows the standard workflow: define the mandrel geometry, set the winding parameters, calculate the path, correct for coverage, and export the CNC program. But there's a catch. The algorithm for tape layup is relatively simple. It assumes the tape follows the surface in a single plane. That works well for narrow tapes on smooth surfaces.
But not for this compensator.
Not exactly. On the crests of the extreme corrugations, the algorithm fails to display the wide rubber tape laying tightly against the generatrix. Instead, we see artifacts, what we affectionately call ribbons of bows or ruffles. The tape appears to bunch up or ripple, which is not what happens in reality.
Why does this happen?
The reason is the simplified bending model. The current algorithm does not account for tape bending in two planes simultaneously. When the tape is wide and the surface curvature changes rapidly, as it does on the corrugation crests, the program can't accurately predict how the tape will conform. So it creates these visual artifacts.
Does this affect the CNC output or the actual layup process?
Importantly, these visual inaccuracies do not affect the functionality of the generated winding program or the actual implementation of the rubber tape layup. The underlying path calculation and G-code generation remain fully valid. The artifacts are purely a limitation of the visualization model, not of the manufacturing process.
So the engineer can still use the program to generate a working CNC program.
Absolutely. The example is somewhat conditional. It's a demonstration of the capabilities and current limitations. It shows that WinderCAM handles the standard tasks well, but also points to areas where the algorithm can be improved. The ruffles are not a defect in the output, they are a visual indication of where a more precise model is needed.
To make the visualization more accurate, we need to account for bending in two planes.
Yes, sir. A more advanced model of tape deformation in two planes would allow the algorithm to predict how the wide rubber strip actually conforms to the corrugated surface. This is a direction for future development. But again, the current version already produces a fully functional CNC program. Rubber cord compensators are used in large diameter pipelines for oil, gas, and chemical plants. They absorb thermal expansion, reduce vibration, and compensate for misalignment between pipe sections. The combination of rubber elasticity and cord reinforcement gives them excellent durability.
This example shows that even for non-standard materials and geometries, WinderCAM provides a solid foundation.
Yes, sir. And the next step is to refine the model for wide tapes on complex surfaces.
Thank you for watching. Stay tuned for the next example.